Monday, guys. Good morning. Let's keep going with 2.7. My hope is to finish it by the end of today's video. And again, just to kind of give you a lay of the land here. So last Thursday when we had live class, I misspoke to the first hour, and I was talking about how, hey, we're going to have a test on Monday. But then I completely forgot that we were already switching gears next week, Monday. Next week, Monday, is conflict res for Group A, a third of you about. Again, we're kind of in this weird hybrid model now moving forward starting next week. So we'll have an A group, a B group, and a virtual group. But yeah, so next week, Monday is kind of weird because some of you will be here and we'll be doing conflict res down in the field house. But anyway, so the test is not next week, Monday. That's not going to work. We'll have an in-class review tomorrow. We'll have a test on next week, Tuesday. Again, this week is kind of a dead week. We have conferences on Wednesday, so that means we don't have class because on Wednesday our classes wouldn't have met until 1 or 2. So I'm not allowed to give you guys anything on Wednesday. Thursday, Friday is professional development. Then next week, Monday is conflict res. We're starting the hybrid model with some of you here. So we'll take a test on next week, Tuesday. Okay, so very, very strange. Again, everything's posted. All the old videos are posted, all the review sheets, all the answer keys, everything will be on It's Learning. But it's also a big gap. So it's kind of on you guys to make sure that you're studying and staying on top of things and making sure you still know these things a week from tomorrow. But anyway, let's finish 2.7. Finally, it's only taken 6 or 7 days, but it is what it is. I'm okay with that. So let's look at these three. These are some examples. We skipped these last week, and I skipped all the way to the table at the bottom of this page. Let's go back, let's do these, and now using the table or referencing the table, these will be even easier than they would have been prior to looking at that little table that summarizes hybridization. Okay, so under each diagram, write the proper hybrid notation and the proper shape name. So the first one here, this is linear. Ooh, that's not calibrated. Sorry, guys. Alright, I've just wasted 8 seconds of your life. Okay, I can hear a joke in the background. Somebody saying, no, you've wasted way more than that, Mr. Barasan, but that's rude. It's Monday. Be nice to me. Come on. These are all hypotheticals, of course. Anyway, there's the first one. This is linear. Okay? A linear molecule is going to have what's known as sp hybridization. Alright? Again, the table on the bottom of this sheet is everything. Okay? The shape will tell you the hybridization. The coordination number will tell you the hybridization. Okay? So really, if you know the shape of the molecule, or if you know the the coordination number of the molecule, you can identify the hybridization just from that. Okay? The next one, you can see we've got like 2 3-dimensional pictures. These are trying to show like the hybrid orbitals. Okay? But again, let's look at the shape here. That looks like a trigonal planar arrangement. And if it's trigonal planar, this is going to be sp2 hybridized. And again, the naming of those hybrid orbitals is coming from how many s orbitals did you use, how many p orbitals did you use, and it's pronounced sp2. Okay? The superscript 2 is representing how many of that type of orbital was used to blend or hybridize the hybrid orbitals. Okay? The next one, this is tetrahedral. And this is sp3 hybridized. All right, so just a visual of kind of how to identify that in some cases. Draw the Lewis dot structure for ammonia. Okay, ammonia is NH3. Total valence electrons that we have to work with. We have 5 from the nitrogen, 1, 2, 3, because each hydrogen has 1, so we've got a total of 8 electrons to work with. And I'm going to put nitrogen in the middle. I'm going to spread my hydrogens out. That required 6 electrons. I've got 2 left to add. Those have to go on the center because hydrogen can't take any more. Okay? So there is my Lewis dot diagram, or my Lewis dot structure, or my Lewis structure for ammonia. What is the valence orbital diagram of nitrogen? It's been a while. This is Unit 1 stuff, but that's okay. Let's tie it in. The valence orbital diagram. So an orbital diagram is this thing, right? So I'm going to skip 1s. We technically have 1s over here, but we don't really care about that because that's not valence, right? We only care about the valence electrons. So we have 1, 2, 3, 4, 5 electrons for nitrogen. The nitrogen in ammonia has one lone pair of electrons, and the shape of ammonia is, ooh, that's a tough one. What is the shape of ammonia? Well, what's the coordination number, right? Let's go start there. So the coordination number is I have 3 atoms, one lone pair around the nitrogen. That's coordination number 4. And I don't have 4 atoms, because again, 4 atoms makes that tetrahedral shape, right? What I have is 3 atoms and one lone pair. So I have removed, you can think of it as like the top atom off of our molecule. And what's left? What would we describe the shape of the rest of that as? It's a trigonal pyramid, right? So a coordination number of 4 with one lone pair is a trigonal pyramid. Sorry, I'm trying to cram it in that little space. Which makes the nitrogen of ammonia something hybridized. Well, how can we figure out the hybridization? It is all about the coordination number. Coordination number of 4 equals sp3. Coordination number of 3 equals sp2. Coordination number of 2 equals sp. So, the coordination number is 4. That means it's sp3 hybridized. Okay, show the hybridization of nitrogen's orbitals. Sure, we can do that. So again, this is what we did last week, Thursday. Here's where we started. I have 5 valence electrons for nitrogen. What I'm going to do is hybridize these, blend these. I'm going to blend all 4 of those, because it's sp3, right? I need all 4 of those as a part of the hybridization process. And what I get are 4 equal energy, 4 equal energy sp3 hybrid orbitals, okay? I still have 5 electrons, right? So 1, 2, 3, 4, 5. Well, hold on, does that make sense? It does. Think about this, right? How many bonds does the nitrogen make in ammonia? It makes 3, right? We have 3 unpaired electrons in our hybrid orbitals. All right, that's cool. That kind of adds up. How many lone pairs does the nitrogen have? 1. Here it is. This right here, that's the lone pair. Okay? The coordination number is still 4, right? We still have what would start as like a tetrahedral shape, but now instead of having 4 bonds, because we don't have 4 electrons to share, right? We just have 3 unpaired electrons. The 4th spot, or the tetrahedral spot facing upward, if we orient it that way, is a lone pair of electrons. And that's because one of our hybrid orbitals is full. It has 2 electrons already in it. So, again, just to recap, the hybridization is coming from the coordination number, okay? That's what's going to give us the answer, so to speak. All right? So let me keep going here. So here's a picture of the way that would look. You can see the tetrahedral shape and the overlap to make these bonds. And let's go to water. Let's do one more of these kind of unique ones, okay? We've done water before. This is H2O, obviously. Total valence electrons to work with is, again, 8, same as the ammonia, actually. Oxygen's in the middle. I need a bond to each of my hydrogens. When I do that, that required 4 electrons. I have 4 left to add. Hydrogen can't take any, so they all have to go on the oxygen. And that's my structure. The valence orbital diagram for oxygen looks like this. Okay, 6 valence electrons. The oxygen in the water has blank lone pairs of electrons. It has 2, right? 1, 2. And the shape of the water is bent, which makes the oxygen in water blank hybridized. Well, What's the coordination number? How many things are we separating in three-dimensional space? We have 2 atoms, 2 lone pairs. That's a coordination number of 4. When the coordination number is 4, the hybridization is sp3. Okay? Can we show that? We could. Didn't I ask you to do that? I asked you to do it on ammonia. Why didn't I ask you to do it on water? Well, I'm going to make you do it either way. I'm going to do it. You can watch me, I suppose. That's where we start. If I hybridize these, I am going to go to sp3. I'm going to use all 4 of these, the s and the 3 p's, to make this happen. And it's going to look like this. I have 2 electrons still free. I have 2 orbitals filled with pairs. So I'm going to make 2 bonds for the oxygen, and I'm going to have 2 lone pairs as well. So again, the hybridization comes from the coordination number, right? Even though in these last 2 examples of ammonia and water, this only has 3 bonds, this only has 2 bonds. Don't just count the atoms to figure out the hybridization. That's not how we do this. We figure out the hybridization using the coordination number. The lone pairs matter in terms of hybridization. We have a coordination number here of 1, 2, 3, 4, which makes it sp3. Okay? So it looks like this. There you can see the tetrahedral shape of around the oxygen, right? These big purple blobs and blue blobs are representing the orbitals. So again, when a bond is made, these orbitals of the hydrogen over here and the orbital of the oxygen over here are overlapping, and there's electrons shared between them. These lone pairs are in the other 2 orbitals, and we get this bent shape. So again, here's the table. We looked at this last week Thursday, but this is the takeaway, right? This is what you need to know. This is everything you need to know about hybridization. Identify the shape or the coordination number, and that'll give you the hybridization, okay? If there's 4 things separated, it's sp3. If there's 3 things separated, it's sp2. If there's 2 things separated around your atom, it's sp. It's as easy as that. This is everything you need to know. All right, so I could talk about molecular orbitals here, and I'm going to talk about just a little bit. This is a topic that's, again, I'm going deeper than I need to go in this note sheet for what you need for AP Chem, okay? But hang with me for just a second, and kind of like the hybridization stuff, I'm going to give you a takeaway or precisely what you need to know. And I might kind of gloss over some of this because it's really not overly important that you know much of this, okay? It just isn't. This gets, again, like everything in this class, this gets way more complicated if we kept going with it, but there's just not a need to go too far, okay? So when atomic orbitals overlap in covalently bonded molecules, there are 2 ways of describing the nature in which they overlap that AP requires you to know. Those 2 types, or these 2 types of covalent bonds, are called sigma bonds, with this little sigma symbol, and pi bonds, with the pi symbol, okay? Now, this is not 3.14 blah, 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 okay? We're not in math class. Pi in chem, or pi bonds in chemistry, have absolutely nothing to do with that constant, okay? Just a side note. I don't think your brains would have gone there anyway, but just to be sure. So you need to know how sigma and pi bonds relate to single, double, and triple bonds in AP Chem. All right. Basically, and we'll do this at the end of the class, you need to identify when a covalent bond is a sigma bond, and you need to be able to identify when a covalent bond is a pi bond. Okay. So basically, all you need to be able to do is call covalent bonds either sigma or pi, and it's actually really simple to do. It really, really is, okay? So I have an example here, okay, and I'm going to go through multiple examples, but again, the end takeaway should be pretty simple when we get there. All right, so when diatomic fluorine is made, each fluorine shares one of its 7 valence electrons. Okay, so I'm using X's this time on the right-hand side. I've never done that, but I'm just showing you that, like, hey, these are the shared electrons. One of those shared electrons in the bond came from this fluorine. The other shared electron in that bond came from the other fluorine, right? Okay, so that's just kind of a way of visualizing that. So ethene has 2 carbon atoms with a double bond between them, okay? does it make sense that all 4 of these electrons in these 2 bonds can hang out between the 2 carbons? In other words, I have 4 electrons to make 2 bonds. Does it make sense that they can all fit in between those 2 nuclei? I mean, that sounds like it's going to be pretty tough to do, right? We know electrons repel, and they repel pretty strongly. So if we have 4 electrons trying to occupy the same space, there's going to be a lot of repulsion there. That doesn't really make sense, right? So what actually happens, and what we're going to talk about a little bit, and again, we'll get into the end takeaway a little later, but these 4 electrons probably aren't all going to be occupying the same space between the 2 nuclei. That's going to be too much repulsion. What actually happens is more like this, okay? The first bond between the 2 nuclei happens directly, the first bond between these 2 atoms occurs directly between the 2 nuclei, right in the middle between the 2 atoms, like we would totally expect, right? There's 2 electrons, they're shared, a nucleus on either side, an atom on either side, and that makes our first chemical bond. The second bond, the double bond, because again, this molecule, ethene, does have a double bond, carbon, carbon, 2 bonds between them. The double bond actually occurs like way above and way below the 2 nuclei. It's still technically like between them, right? This dot and this dot are technically like between the nuclei, but the electrons are located like substantially above and substantially below the atoms here, okay? And this is what's known as a pi bond, all right? So let's give a little more, okay? So when orbitals overlap directly, meaning like, hey, here's one orbital, hey, here's the other orbital, bam, they overlap head on head directly into one another. We call this a sigma bond. When orbitals overlap sideways, we call this a pi bond. Okay? Pi bonds prevent the molecule from being able to rotate along that bond. We have not talked about bond rotation or molecular rotation at all, but if I have a single bond between 2 atoms, that can actually twist and rotate with no problems whatsoever. Okay? So you can think of it as like, you know, you can spin it, right? You can have one atom just spinning if you'd like. But when you have a double bond, or when you have a pi bond, which a pi bond is going to happen like above and below the 2 atoms, it locks it in place. That bond can no longer rotate along that axis. Okay? Ethane is a carbon chain of 2 atoms. And by the way, I wouldn't expect you to know that, okay? So this is organic chemistry just for a little bit again, or we're using organic chemistry, I should say, to teach what I need to teach. But ethane has 2 carbon atoms. The bond order of ethane is 1, meaning there's a single bond, and it can rotate because of the sigma bond. I'm going to draw the sigma symbol, okay? That's how I draw it. You can see the official drawing of it 2 slides ago, okay? Right up here, right? There it is. That's how sigma looks. When I draw it, kind of looks like that. Sorry, that's just the way it looks. But anyway, so we have 3 organic molecules that I'd like to go through today. Ethane, ethene, and ethine. Okay? Ethane is 2 carbons with a single bond. And with those single bonds, we actually have 3 hydrogens on either side. Ethene is a carbon-carbon double bond. And there's 2 hydrogens on either side. Now, here's the deal with carbon. I haven't explicitly told you this yet, but when you've got carbon, carbon makes 4 bonds. Almost always. I would say 99% of the time, carbon will have 4 bonds. Okay? So in the first one, it's a single bond between the carbons, so it needs 3 other bonds, and those are all going to be to hydrogen. In the second one, ethene, we have a double bond between the carbons, which means we need 2 more bonds to hydrogens on the outside. For ethyne, this is a triple bond between 2 carbons, which means there's 1 hydrogen on either side. Okay? What is the geometry that each carbon has in these 3 examples? Let's look at the coordination number. In the first example, the carbons have 1, 2, 3, 4 atoms around them, right? So if I look at the left-hand carbon, this carbon has 1, 2, 3, 4 atoms to separate. What is the geometry of coordination number 4? It's tetrahedral. Okay, what's the hybridization if we have a coordination number of 4? sp3. Okay, hybridized orbital diagram. You would have something that looks like that. Okay, ethene. What is the geometry around each carbon? Well, what's the coordination number around each carbon? You have 1, 2, 3 atoms that you need to separate. Coordination number of 3 means a trigonal planar geometry. Hybridization, if the coordination number of 3 is sp2. So how would we hybridize this? Well, we would hybridize 1 s and 2 of the p's, but the other p orbital would not get hybridized. It's going to look like this. Ay, ay, ay. I would still have a 2p orbital unhybridized in that second example, okay? Because of the geometry, because of the coordination number, we know that this is sp2 hybridized, right? A coordination number of 3 and a shape of trigonal planar means sp2 hybridization. So we've taken 1 s orbital of the carbon, 2 out of the 3 p orbitals from the carbon, and blended them to make these 3 hybrid orbitals of sp2. However, that means we still have 1 unhybridized p orbital. Okay, so that's what I have. I have to draw that. The last one here, ethyne. What is the geometry around each carbon? Well, what's the coordination number? How many atoms are attached to each carbon? The answer is 2. So what's the shape? It's linear. Coordination number of 2 is linear. What's the hybridization? sp. How does that look? I would have 2s, oops, gosh, I can't write s's and 2's. I would have 2 sp hybrid orbitals, and I would have 2 unhybridized 2p orbitals. Like such. Now, why does that matter? Okay, here's what happens. The first bond between the carbons, like in ethane, is a direct overlap of the hybrid orbitals. It's a sigma bond. Okay? The second bond and the third bond between the carbons to make ethene and ethyne is going to occur between the p orbitals. And these are going to be pi bonds. I've got a bunch of pictures. Okay? So in this slide, here's my carbons. This is ethane. I have 3 hydrogens. Each carbon is sp3 hybridized, and they make a nice tetrahedral shape with these purple orbitals. Okay? Bond number 1 happens when this hybrid orbital from this carbon and this hybrid orbital from this carbon overlap. These are both sp3 hybrid orbitals. That's the first bond. The next bond that happens, okay, and I'll kind of show you that. This is ethene. Ethene has the first bond right here overlapping directly with the hybrids. By the way, this is sp2 hybridized, right? So we have a trigonal planar shape for these now. Okay, I have these 2 sp2 hybrids overlap directly to make the first bond, but the double bond happens If I flip this whole thing on its side, okay, you can kind of see this happening. They've taken this, which is now like flat, okay, if you can see my little video in the corner, and they've taken it and gone like this. They've flipped it on its side. We still have p orbitals on each of these carbons. The p orbitals would be pointing perpendicular to the hybrid orbitals. The hybrid orbitals are the flat trigonoplanar ones, and the p orbitals would be up and down, above and below either carbon like this. The second bond, the double bond, occurs when these p orbitals, these unhybridized p orbitals, overlap above and below the plane of that first bond. This is getting rather abstract. If you're hanging with me, awesome. If I'm confusing you, don't worry. We'll make life much easier in just a second. For the triple bond, these are sp hybridized. I have sp hybrid orbitals facing along this plane. We have a nice linear molecule, hydrogen, carbon, carbon, hydrogen. The first bond is right here. It's a direct overlap between sp hybrid orbitals. Bond 2 and bond 3, to make this triple bond, occur when the p orbitals above and below, they're calling these pz for the z-axis, don't worry about that too much. When the above and below, up, down, p orbitals overlap, we get our double bond. And then we have these in-out, okay, p orbitals. They're calling them py. These can overlap as well. So we had two hybrid orbitals for these carbons in the triple bond, but then we have two p orbitals that are unhybridized. We can overlap and make triple bonds this way. Okay, I'm done trying to do this anymore because it is confusing. So let's just get to where I want to go. Here's the takeaway. If the bond order is 1, in other words, if you have a single bond, you always have a sigma bond. Okay? The very first bond, the first bond in any molecule between any two atoms ever, anywhere, is sigma. Okay? Single bonds are sigma bonds. If the bond order is 2, you always have a sigma bond because the first one is always sigma. And you have a pi bond. Okay? Bond number 1. The first bond between any two atoms in any molecule anywhere is always what we call sigma. The second bond, if it's a double bond, is pi. If the bond order is 3, you always have a sigma bond. Again, two atoms, first bond between them is always sigma. If you have a double bond, the next one is pi. If you have a triple bond, the third one is also pi. All right? That is the takeaway. When molecules are made and any bond happens between any two atoms, the first bond is always what we call sigma. Any double or triple bonds, the second or third bond after that point is always pi. All right, so let's try this very last problem, and then we'll be all done with 2.7. In this last problem, I have a very strange looking molecule over to the right. This is aspirin, okay? Now, this isn't perfect because it's an organic chemistry way of drawing aspirin, okay? So let me help you, all right? Let me help you and draw this a little better for what we know in AP chemistry, all right? Let me fix some things. If you look right here, this says H3C. What that's really trying to say is that there are 1, 2, 3 hydrogens attached to that carbon. That's what it's trying to say. Okay? We also have missing lone pairs all over the place. So each of those oxygens should have 2 lone pairs. If you notice as well, up top here, I have OH. That really just means there's a hydrogen bonded to that oxygen, right? So let me go like that instead. We also have missing hydrogens on this molecule. okay, every one of these intersections, okay, of these lines represents a carbon. This is a carbon, this is a carbon, 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 okay? And then last but not least, we are missing hydrogens right here, right here, right here, right there. That's a better way of drawing it for us. In organic chemistry, we kind of ignore some of the hydrogens, we ignore some of the lone pairs, because that's usually not what we're focused on if you're doing organic chemistry. Okay, so here's what I'd like you to do. I'd like you to pause the video and try to answer these questions. How many sigma bonds are there in this molecule? Remember, if it's a single bond, or I should say it this way, the first bond between any two atoms is always sigma. So all I'm asking you to do is count. How many sigma bonds are there between all of the atoms in this molecule? The first bond between any two atoms is always sigma. How many pi bonds are in this molecule? The second bond between any two atoms is always pi. We don't have any triple bonds, so we don't have to worry about triple bonds, but if we did have a triple bond, again, first bond is sigma, second bond is pi, third bond is pi, if we had that. We don't, okay? How many carbons are sp3 hybridized? Well, how could I answer that question? How do I answer the hybridization question? It's all based on coordination number. That's it. I have coordination number of 4, that equals sp3. If I have a coordination number of 3, that's sp2 hybridized. If I have a coordination number of 2, it's sp hybridized. Same thing for the oxygens. How many of these are sp3 hybridized? How many of these are sp2 hybridized? Okay, that's a lot. I'd like you to try it. Please try it. See if you can answer this. How many sigma bonds are there? How many pi bonds are there? How many carbons are sp3? How many carbons are sp2? How many carbons are sp? And then how many oxygens are sp3? How many oxygens are sp? Go for it. All right, hopefully you paused it. I hope you tried it, but let me walk through how I would do this. Okay, I'm gonna just like tally up my bonds here. So the first bond is always sigma, right? All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I missed one. 21. I think we have 21 sigma bonds. Pi bonds, that's the double bonds, right? The first one here was sigma, the second one is pi. The first one here is sigma, the second one is pi. So 1, 2, 3, 4, 5. 5 pi bonds. sp3 hybridized carbons. This carbon right here has a coordination number of 1, 2, 3, 4. That's sp3 hybridized. This carbon right here has a hybridization of 1, 2, 3. Or I'm sorry, it has a coordination number of 1, 2, 3. There's only 3 atoms. That's sp2. The carbons in the ring, every single one of these is sp2 hybridized because they all have a coordination number of 3. This carbon right here, 1, 2, 3. This carbon right here, 1, 2, 3. So on and so forth. Every carbon in the ring is sp2 hybridized. The carbon up top here, 1, 2, 3, coordination number is 3. We only have one sp3 hybridized carbon, and that's this guy way on the left-hand side of the molecule. Okay? It's the far left-hand carbon. That is sp3 hybridized. It has a coordination number of 4. Every other carbon has a coordination number of 3, which means the remainder, 1, 2, 3, 4, 5, 6, 7, 8, are all sp2 hybridized, and we don't have a single sp hybridized carbon. An sp hybridized carbon would be only a coordination number of 2. None of our carbons have a coordination number of 2. They all have at least 3 atoms attached. Oxygens, how many of these are sp3 hybridized? Well, we're looking for oxygens with a coordination number of 4. Remember, lone pairs count, right? So let's look at this. This oxygen down here on the bottom, it has 2 lone pairs and 1 atom. That's coordination number of 3. This oxygen right here in the middle, before we get to the ring, has 1, 2 atoms, 1, 2 lone pairs. All right, that's sp3. That is a coordination number of 4. The other two oxygens, this one up top with the double bond, is a coordination number of 1, 2, 3. The oxygen on the end is a coordination number of 1, 2, 3, 4. It's bonded to a carbon and a hydrogen for 2, and 2 lone pairs for 2 more. So it looks like we have 2 of each. The double bonded oxygens are sp2 hybridized. They have a coordination number of 3. The single bonded oxygens with 2 atoms attached are sp3 hybridized because they have a coordination number of 4. Okay, that was a lot. I hope this kind of makes sense. Again, we'll be reviewing tomorrow. I would strongly recommend that you start taking a peek at your review packet, not the in-class one, but the other one. And I'll be posting that answer key very shortly here in the near future. So if you need any help today, please let me know. Otherwise, have a great day. And we have finally finished 2.7. We made it, guys. All right, I'll see you tomorrow. Have a great day.